So we're moving into this chapter, chapter 9. This is a long chapter. We'll start with a discussion of basically the Otto and diesel cycle, which model internal combustion engines. Do you ever pop the hood of your automobile? Have you driven in an automobile, ridden in an automobile? Sure. You know what makes it work? Probably half of you or more of you are in, aspiring mechanical engineering majors because of automobiles. I did lots of, polls of students that said, why did you pick mechanical versus civil or electrical? And a lot of them will say because of engines and automobiles. And these are quite complicated devices. They're probably in the top 100 inventions in the last 100-some years. I know it's over 100 years now we've had internal combustion engines moving vehicles. But it's a big, big contribution. So as a mechanical engineer, please don't graduate with a degree in mechanical engineering and not know something about gasoline and diesel engines, internal combustion engines. So go to YouTube, look at some animations. They didn't have these type of things when I was a student. They are excellent. I'm just going to show one. Hopefully it'll play. It's this one. It's probably made by a student. It just is a 4-stroke engine, a working animation.
A basic lesson in the fundamentals of a 4-stroke EFI gas. Now, that's fast. Let's see it again. Amazingly, the 4-stroke EFI engine does this smoothly, quietly, and reliably for years and years of operation.
I didn't have the advantage of any of these videos and the internet when I was a student. They really help. What are the 4 strokes? Well, the little video we showed just showed them. Let's do this. We have a piston, I've showed it in red, sitting here at the top, and it's going to go to the bottom inside the cylinder, slide down. Why? Because it's connected to a crankshaft that rotates around the middle of the crankshaft, but it's connected at an offset. And so that offset moves, and as it moves 180 degrees, it moves from top dead center to bottom dead center. That is 1 stroke. 1 stroke. Now, if you had an intake valve and it was open during that stroke, it would be creating a vacuum, yes, lower than atmospheric pressure, and it would draw air and fuel mixture, if the fuel injector added the fuel to the air, into that cylinder. It would draw it across the air filter, through the tortuous path of the ducting and the intake manifold, and there is some pressure drop that it has to draw it across that open intake valve. So yes, this is at a state of a vacuum during the majority of that intake stroke. Maybe as it starts, it's still not at a vacuum. It has to pull down enough to make it a vacuum. But that's our intake stroke. Okay, I can spell take. Okay, great. Then we have the intake valve closes. You go through another 180 degree or half a rotation of the crank, and that is our compression stroke. Now you have trapped at a very small volume at the top an air-fuel mixture. You have a little spark plug typically up here. The engine control module sends a little spark, boom, it combusts, and then you have the expansion pushing down high pressure, high temperature exhaust products, and now you have a power stroke. All right? At the end, you crack open the exhaust valve, and you have 1 stroke where it's trying to push out most of the exhaust products. That's called the exhaust. So intake, compression, power, exhaust stroke. Those are the 4 strokes. What does the piston do? This is one of the strokes, then another stroke, then another stroke, then another stroke. 4 strokes. So we talk about the location of the piston. We use these acronyms. TDC, top, dead, center. And then BDC, bottom, dead, center. Then back to top, dead center, bottom, dead center, top, dead center. That's one of those strokes. Then you think again, what is the name of this stroke? Intake, then compression, then power, then exhaust. Just repeat these things. Memorize these things if they're brand new to you. It'll help you put it all together. And then you think about what is happening with that valve. Well, we have an intake valve that's open at the beginning of the intake stroke and then closes at the end of the intake stroke. And then the intake and the exhaust valve stay closed all through the compression and power strokes. But the exhaust valve opens at the beginning of the exhaust stroke and closes at the end. So right here there's this overlap where the exhaust is closing and the intake's opening. Well, let's talk about a pressure volume diagram. Pressure on the y-axis, volume on the x-axis for a true four-stroke gasoline, type of spark ignition internal combustion engine. What we want to do is put a line right here, and that's atmospheric pressure, because sometimes the pressure inside that cylinder is below atmospheric pressure. That's how you draw in the air across the air filter and through the valve intake structure. Okay, let's do this. Let's also draw it where that's the maximum volume. This seems a little backwards, but this is the volume when the piston is at bottom dead center. That's my maximum volume. And then the piston goes to top dead center, and then that's my volume at top dead center. So the piston's sliding back and forth between top dead and bottom dead for those strokes. Let's start thinking that the air is around atmospheric pressure at bottom dead center, and it's beginning, not the intake stroke, let's begin with the compression stroke. So as you compress, there's no valves opened, and it's going to lead to a rise in the pressure, and somewhere around in here, before top dead center, a few degrees, it's controlled by your distributor mechanically. It used to be, now it's all electronically controlled. It senses when it should be, firing that spark plug. Often at idle, maybe it's set at 12 degrees before top dead center. Anybody use a timing gun? Yeah, and you set it with the mark of the crank, but now that's kind of old school. But used to have to rotate the distributor. Now that's kind of gone. All the controls, electronics. But it fires a little bit before. Now, if you're running at 5,000 RPM or 10,000 or 8,000 RPM, it could be firing 40, 50 degrees before top dead center. It's going so fast. But those are changing. But let's think it fires a little bit before top dead center. It leads to a rapid increase in the pressure because of the combustion. Huge heat release. It's all trapped to a small volume. Temperature goes way up, pressure goes way up. But then it's going to be expanding through the power stroke. And as you expand through the power stroke, you get down to where another valve cranks open. That's the exhaust valve. Now, this is why you have mufflers. Some of you don't. You drive by my house maybe a mile away, and I can tell you don't have a muffler. But this is why, because when that exhaust valve cracks open, this pressure is much higher. And it can create choked flow, Mach 1, right through the passage of that exhaust valve, and it makes it really loud. Really loud. Now, that also leads to a very rapid reduction in pressure when that valve cracks open, because a lot of gases get out. But there's still some gases in there, even though the pressure is now reduced to just a little over atmospheric pressure, and you have to push them out. And as you push them out, you have to push it through the valve, through the exhaust manifold, down in the piping, through the muffler, there's some pressure drop there, through the catalytic converter, and finally out the tailpipe. So the gases are at more than atmospheric pressure as you're pushing them out and finally dumping them outside your automobile. Now, you get over here, you turn it around, and now you don't have any more exhaust stroke. You have the intake valve open. You close the exhaust valve, and now you're doing what? You have an intake stroke, and it's a sense of vacuum. It's a below atmospheric pressure. That's how you draw in that air across your intake air filter and intake manifold, etc. So this would be a good diagram. If you had a good pressure sensor in the cylinder, you could measure that and then plot it. And yes, they have the capability to high-speed data acquisition to do that and generate these plots. So this is kind of the compression stroke. This is your power stroke. This is your exhaust stroke. And this is your intake stroke. Now that's pretty complex. What we want in this class is to have a very simple model for this, something that we can analyze using the very simple equations that we learned in Thermo 1 and expand here in Thermo 2. Before I do that, I need to make sure and talk about what stroke is. Stroke, letter S, symbol, and then bore, cap B. All right, the easiest one probably is bore. What is bore? It's the, looking down at it, it's the diameter. The bore is the diameter of the cylinder, which there's negligible difference between the diameter of the cylinder and the diameter of the piston. Yes, the piston has to slide in between or inside the cylinder, but it's just a small difference. You just call the bore the diameter of the piston, the diameter of the cylinder. Okay. And then the stroke is how far it goes from top dead to bottom dead center. The distance that the top of the piston travels, or you could think about the middle of the piston, whatever. As I've shown it, it's kind of the distance that the top of the piston travels from top dead to bottom dead center. That's the stroke. Now, you look at the crank, and if somebody had a crank and they had the offset is the distance away from the middle of the crank that the connection is made. The connecting rod connects to it. You could have one where you have a large offset or a small offset. This actually determines the stroke, doesn't it? So right here, can you see that that distance is the offset? Let's call it A. And likewise, from the middle up, that's the offset A. Can you see what is the relationship between the stroke and the crank offset? 2A, yeah. And so you want some engines that have are designed for very high RPM. They'll have a small crank offset, and they'll have very small strokes. But then some that are huge, they're running at maybe 60 RPM. I know some vessels, ocean-going vessels that use big diesel type of engines. You can look on the internet and see what's the biggest engine out there, and they're huge. They're going to go slow, and they're going to have a big stroke, long stroke, a big crank offset. All right. Also, we want to talk about clearance volume and displacement volume, and the volume at top dead center and the volume at bottom dead center. So here, the piston's at top dead center, and this volume right here is the clearance volume. And it's also the volume at top dead center. All right. Now, when you're at bottom dead center, the gas occupies this volume plus, I tried to shade it different color, this volume. So the volume at bottom dead center is the clearance volume, the volume clearance, plus what is the displacement? What is that stroke? How much is swept through by the stroke? And that is called the displacement volume. All right. So you look at it, what's the relationship between the displacement volume and the bore and the stroke? Well, it would be the stroke, this distance, S, times pi bore squared over 4. Is it that my surface area of the face of the piston times the stroke? That gives me the displacement volume. Now, if I add the displacement volume and the clearance volume, I get the total volume at bottom dead center. All right. So somebody said I have a 2-cylinder or a 2-liter engine, right? And they said it's a 2-liter engine and it has 4 cylinders. So I take the 2 liters, I divide by 4, and I'll have the volume displacement for each cylinder is 0.5 liter. That's not the same as the volume at bottom dead center. It's just that swept volume, the displacement volume. That's what they're reporting. All right. So somebody said I had a 5.7 liter 8-cylinder engine. Well, you can find what is the volume for each of the cylinders. All right, that's the displacement volume. The last is a compression ratio. This book uses a symbol R, no subscript for a compression ratio. And it's basically pretty easy to understand. You take all of this volume that's occupied at bottom dead center and you cram it only into that volume at top dead center. That's the compression ratio. The compression ratios may be 10, or they'll say 10 to 1, or 9 or 9 to 1. They'll describe it like that. But here, it's the larger volume, the volume at bottom dead center, divided by the volume at top dead center. And gasoline engines are typically around 10. How many people know the compression ratio of their engines? What do you have?
On the bike, it's like a 12.
Oh, is it 12? You have to have a high octane fuel? All right. Anybody else know it? Really? Not that many gearheads? 10.5? Yeah. I think mine is around 9.5. But if you push up around 11.5, 12, you're going to have to go for that premium grade fuel. If you don't have a high compression ratio engine, you don't need the premium grade fuel. Go with the lower octane. All right. We want to do an analysis of a very complex problem. So to do an analysis, we basically introduce some simplifications. So we introduce what every textbook in engineering thermodynamics calls air standard analysis. These are the assumptions which make calculations doable. It's not that it's more accurate, it's just that we still get the essence, we can still make good predictions, we still can describe the behavior, but we have to make some approximations. So we focus on a fixed amount of air that's trapped in the piston cylinder. Already it's trapped. You can think about it. You're going to do a closed system analysis, a control mass analysis, not an open system. All right? So it's trapped in a piston cylinder. It's always air. There's never converted because of the combustion to CO2 and water vapor. It's just always air. And it always behaves as an ideal gas. This is probably the hardest one that people have to remember out of Thermo 1. They'll remember, oh yeah, PV is equal to RT. Let me put this clearly as a specific volume. Isn't that the ideal gas equation? That's absolutely true for an ideal gas. But also, U is a function of temperature only. That's a lot different than what we had for steam. Superheated steam, if I want to know the internal energy of superheated steam, I need to know temperature and pressure. Do I need to know pressure for the internal energy of air behaving as an ideal gas? No, you do not. All you need to know is temperature. That you need to think about. If you haven't already struggled with that out of Thermo 1, struggle with it now, because I get a lot of questions and it goes back to that fact right there. Now, if H is defined as U plus PV, is that the definition of enthalpy? And I can replace PV by RT from that first equation. Then I have, get this out of the way here. Okay, it won't move, fine. I have a function of temperature only plus a constant times temperature. Function of temperature plus a function of temperature is only a function of temperature. H is not a function of temperature and pressure. It's just like U. It's only a function of temperature for an ideal gas. So those three things, please remember. Now, combustion is complicated. What we're going to do is replace it by a heat transfer from an external source while the piston's at, hey, I forgot, what does TDC stand for? TDC, something. What does TDC stand for? Top dead center. So at that small volume at the top, we're going to replace all that spark plug, complicated combustion by just sit there and heat it up from an external heat source. That's an approximation. And in intake and exhaust, that's all complicated. Just replace all that by the same thing at bottom dead center. You're just going to sit at bottom dead center, have a heat transfer. This time it's not going to heat up the gas, it's going to cool the gas out. And then let's do this. Let's make everything frictionless. Let's make everything internally reversible. That'll help. Now, if they add the word cold in front of air standard analysis, it's everything for the air standard analysis as described above, but in addition, use constant specific heats evaluated at the ambient temperature, 25 C or 298 Kelvin, and I will often just say give it to me at 300 Kelvin, because what's the difference between 298 and 300 Kelvin? Minuscule. But we're using constant specific heat. Somebody may say, well, I'd like some specific heats that are at a higher elevated temperature that capture what's, the average temperature of the gas as it goes through the cycle. Great, call it a warm air analysis and move on, but nobody calls it a warm air analysis except for maybe me. So just know what a cold air analysis means. So that means using constant specific heats where you evaluate them at 25 C. All right. Why do we make this additional simplification? Because we want to make it even more doable, easier. And this still is helpful at analyzing what's happening. All right, so Autocycle, what we're going to do is we're going to have just what we described. We're going to replace. So we start here at a large volume. This is still the specific volume at bottom dead center. And we're going to undergo a compression stroke, and we'll go down to a volume at top dead center. And then we're going to stop. So this is like state 1 and state 2. That's compression. Now we're going to sit there at top dead center. And we're just going to heat it. Well, if you just heat an ideal gas at constant volume, what's going to happen to the pressure? It's going to go up. Then you stop the heating process. That replaces our combustion. And we go through an expansion. That's like a power stroke down to the final state 4. At that state, we then have constant volume heat rejection. That cools it, and we complete our cycle. So this is our PV diagram that helps us walk through the 4 states and the 4 processes. So we'll talk about the process 1 to 2, going between states 1 and 2, and then 2 to 3, and then 3 to 4, and then 4 back to 1 to complete the cycle. What we need to do is a first law and a second law analysis of each of those processes. So from 1 to 2, what was that called? Compression. Compression. So let's write the first law. What does the first law look like? U2 minus U1 is equal to Q1 to 2 minus W1 to 2. Why do I add the subscripts 1 to 2 on the Q and the W? Because we're going to write the first law and for all of these 4 processes, not just 1 to 2, but then 2 to 3, and then 3 to 4, and then 4 to 1. So okay. Now, does that look good for the first law? Is that for a closed system, a fixed amount of mass, a fixed amount of air, undergoing a process, initial state 1 to final state 2? Yeah. Let's do this. Let's go ahead and write the second law. So this is our conservation of energy. This is our second law, an entropy balance. Does it look like S2 minus S1 is equal to? Now this is a little tricky. Del Q divided by T integral. If you had a constant temperature during the process, I wouldn't have to put an integral there. It would just be Q1 to 2 divided by the T at which it transferred across the boundary. A lot of times we'll put a TB there. Fine. And then we have one more term, sigma 1 to 2. Hey, what is this sigma 1 to 2? Entropy generation. So I look at this and then I say, because it's internally reversible, what is sigma 1 to 2? 0. No irreversibilities. It's internally reversible. Okay. I then look over here and I say, during the compression stroke, I'm going to assume that it's adiabatic. What does that mean? Well, there's no time for heat transfer. Okay, if there's no time for heat transfer, then the student that is brand new in Thermo 2, more than half of them will say, You mean if I have a gas and there's no heat transfer, then I know what the temperature change is, 0. Because if it's adiabatic, no heat transfer, then the final temperature has to be equal to the initial temperature. But you passed Thermo 1. You're not going to make that mistake. Right? No way. So yes, this is what's 0 because it's called adiabatic. That does not mean it's isothermal, because when you are compressing it, that work, that boundary work, is going to increase the energy, and U2 will be higher than U1 because of that work, and T2 will be higher than T1. This is a good review of Thermo 1. So just thinking about it for a minute, the way we wrote it, we put a negative sign on this W, so work out is positive, but for work 1 to 2, isn't that negative? Boundary work during the compression is negative. I'm staying with the sign convention. So it's like this. Work 1 to 2 is negative. You put a negative in front of a negative. This is over here. This difference is positive. Hence, T2 is greater than T1. It's going to be hot at the end of the compression stroke. But the math will work itself out. Please check that yourself. Let's come back over to the second law. Because it's adiabatic, what is this term equal to? 0, no heat transfer. So now we see that if the 0 and 0 are on the right-hand side, what is the left-hand side equal to? 0. And so S2 is equal to S1. We conclude that the process 1 to 2 is isentropic. That's exactly right, isentropic. It's constant S. That process 1 to 2 is constant S. All right, let's now go to the process from 2 to 3. That was our constant volume, so volume is equal to a constant heat addition. So we'll have U3 minus U2 is equal to Q 2 to 3 minus the work 2 to 3. Of these 3 terms in this equation, I'm going to call this term A, I'm going to call this term B, term C, clicker question. Which one of those terms is 0 for the process 2 to 3? Is U3 minus U2 0? Is Q 2 to 3 0? Or is work 2 to 3 0? Raj, you making good progress? You going to get them all done? You need to. They're going to pick them up. You need to bring them down here when you're done and put them on the table, spread them out. All right, everybody in? Raj back there is grading your homework portfolio. Your homework portfolio needs to be in to him now. If it's not in, it doesn't get graded, class ends, you won't get a grade. Also, when this class ends, if your exam is not in this stack, you get a 0. It needs to be in this stack. Don't follow me to my office and then try to get it turned in. I'm mean. All right, let's take a look. Absolutely right. Why is that work 0? It's a constant volume process. The pressure is going to go up, but what's the volume do? Doesn't change. The integral P dV is 0. Hence, this term is 0 for constant volume. All right, let's go ahead and write out the second law. We have that S3 minus S2 is equal to the integral del Q over TB plus sigma 2 to 3. Now, I'm just going to say that it's internally reversible. That's 0. This term is not 0, but it's going to be difficult to work with because the temperature is increasing as we continue to heat it. But we do know that S goes up because of that heat transfer coming in. All right, let's go to process 3 to 4. U4 minus U3 is equal to Q 3 to 4 minus the work 3 to 4. Well, what was this process 3 to 4 described as? That was not compression stroke, but are power or expansion. All right, should the expansion be adiabatic? Yeah. Why do we, Professor, you just willy-nilly, this one's adiabatic, this one's isentropic. No. There's negligible time for significant heat transfer, hence we call it adiabatic. We neglect the heat transfer. Yes, sir.
In real life scenario, are we going to assume that it's adiabatic as well?
Yep. In the Otto cycle, that's the standard assumption. And yes, when that engine is moving that fast, you can neglect the heat transfer. Now, if you really want an accurate simulation and you have a lot of computer code power, well, then you can model the heat transfer. And when you take ME 4313, you will be given the tools, if you choose to use them, to actually do a pretty good approximation of analyzing that. But you're going to need to know, like, how long does it take to go from top dead to bottom dead? What's the cylinder wall temperature? What are my gas properties and speeds and conditions in that cylinder? So it's not a trivial problem. It's a pretty complex problem. All right, so this is 0 because it's adiabatic. We do the second law analysis for the process 3 to 4. So we get S4 minus S3 is equal to the integral del Q over TB plus sigma 3 to 4. Now it's internally reversible. It's adiabatic. Hence, we conclude that it is isentropic. Isentropic. So that'll allow us to come back and make further calculations quantitatively for these works and energies. Let's continue on. 4 to 1. U1 minus U4. Isn't the final state U1 and the initial state of the process U4, state 4? So 4 to 1 equal Q 4 to 1 minus work 4 to 1. It's constant volume, heat rejection. We anticipate this Q right here to be negative, just like we anticipated this Q to be positive. Right up there. All right, there's not much you're going to get out of the second law for this process also, so let's leave it alone. Okay, let's write it. S1 minus S4 is equal to the integral del Q divided by TB plus sigma 4 to 1, and it's internally reversible. All right. Now, if I take these 4 equations, I can add all 4 equations up. So it's like I do the sum of these 4 equations. So let me kind of work on this one. What is U2 minus U1, the first equation, left-hand side, plus U3 minus U2, the second equation's left-hand side, plus U4 minus U3, the third equation's left-hand side, plus U1 minus U4. If I add all of those up, what am I going to get? Well, what happens to the U1s? They cancel. What happens to the U2s? Right there. What happens to the U3s? And then lastly, what happens to the U4s? So when I sum those 4 equations, I get 0 is equal to. Now, what do I get when I sum and I get this Q1 to 2 plus Q2 to 3 plus Q3 to 4 plus Q4 to 1? That's called Q net. And then likewise, W net is the sum of the W's. Let me expand that a little bit. So definition, Q net is Q1 to 2 plus Q2 to 3 plus Q4 to 1. Sorry about that. 3 to 4 plus Q4 back to 1. Now half of those terms are 0 because 2 of the processes were adiabatic, but we include them all. And then also 2 of the 2 terms, one was positive and one was negative. All right. And then W net, the same thing. It's work 1 to 2 plus work 2 to 3 plus work 3 to 4 plus work 4 to 1. 2 of them are 0. That's the constant volume heating, constant volume heat rejection. And then the 1 to 2 will be a negative, and the 3 to 4 will be positive. But when I add these up, these need to be the same, right? They need to be the same. All right. All right, let's sketch it now on a PV diagram. and a TS diagram. So pressure, volume, temperature, entropy diagram. I like to work with lowercase s, specific entropy, lowercase or specific volume. Okay, we start at state 1, large volume, low pressure. We undergo a compression process. It's S equal to a constant, so it goes from state 1 to state 2. All right, let's start state 1 right here on a TS diagram. Constant S, where is state 2 in relation to state 1? Above, straight up. Straight up, there's state 2. Now you have constant volume heat addition. Constant volume heat addition, you don't change your volume, but the pressure is going to go way up. Likewise, this is going to go up to state 3. V is equal to a constant, just like S, entropy is equal to a constant for this other process, 1 to 2. All right. Then from 3 back down to 4, I have to get it all the way back down to the same volume. And S is equal to a constant. So we drop it to state 4. And then 4 back to 1. V is equal to a constant. 4 back to 1. So this is our Otto cycle. I'm kind of putting arrows for the directions of all the paths. Why do I put them as solid lines? They're all int rev, internally reversible. Now, the specific work is the integral of P dV, true or false. That looks good. So we can say that the work, let's do 3 to 4 first, is the integral P dV from state 3 to state 4. That's this. Is that work from 3 to 4 the area under the curve from 3 to 4? It sure is. Now, because we're moving in a direction, again, I'm going to try and show it. This direction, I'm moving from V3 to V4, from a smaller V3 to a larger V4. I'm moving in the right direction. Now, the calculus faculty never told you that you could also integrate integral P dV and go from V1 to V2. All right, which is larger, V1 or V2? V1 is large. I'm going in the opposite direction. They never did that integral. But all you have to do is switch and it switches the sign, right? So the integral, the work from 1 to 2 is the integral P dV, but it's going to be negative. And it's visually the magnitude of the area under that curve. So when I do W net, that's the sum of the two works. The other two were 0 because constant volume going from 2 to 3 and 4 to 1. And guess what? That's this. Isn't it? Isn't that the visual image of the net work for the cycle? It's the area enclosed on a PV diagram. If you put in more heat, you push temperature 3 up higher, then it's going to open it up. See, you would have a greater separation, more work net, larger work net for the cycle. But let's not get too confusing right now. Let's go over here. We recall something about entropy and heat transfer. We recall, let's do it this way, del Q is equal to TdS. Or if I integrate both sides, Q is equal to the integral TdS. I know that's a long time from Thermo 1. You forgot your old friend equation here. But you remembered fondly this one, work is integral PdV. Just as fondly, Q is equal to integral TdS. So we think about this one. Think about going from 2 to 3. That's the easier one because it's going from S2, which is smaller, to S3, which is larger. That makes sense from our experience learning calculus and integration. And so This area under the curve, let me try and draw it with blue, is what? A visual image of the Q 2 to 3, the heat addition, and it's positive. All right. Now we change the direction. We're going this way, 4 back to 1, and we have the same equation, Q integral TdS, and we're going to get that the Q 4 to 1 is, this is going to be positive, this one's going to be negative, and it's visually the area under the curve. I take and add them both up, keeping that negative sign such that the area enclosed on the TS diagram is Q net. Is Q net. Remember these things? Very good. If not, hey, we have a whole book that lovely book, you can read it and refresh your memory. All right. Okay. Now we have to remember some things about ideal gases and how to calculate changes in properties like U, H, and S. So somebody says, I have an ideal gas, and it's easy to do constant specific heats. I know variable specific heats, you go to the air table, but simplify it, just go constant specific heat. Well, you recall that U is a function of temperature only, and the definition of C sub V is the rate of change of U with respect to temperature holding V constant, which for an ideal gas, it's not a function of V. I don't even really need to focus on that. It's just du dt, easy to separate, so I get du is equal to Cv dt. I integrate, and I get final minus initial internal energy is C sub V, which is, if it's a constant, comes outside the integral, times the final temperature, T2 minus T1. Look familiar? Yeah. You do the same game. We don't need it for Autocycle. We'll need it for the diesel cycle, so I just show it to you for a change in H. Change in H has C sub P instead of C sub V times the delta T. We don't use it for the Otto. Next time when we get to diesel, we'll use it. All right. But the hard one, somebody says, S2 minus S1. How do I get a change in the S? Well, how about C natural log of T2 over T1? Good enough? Or maybe I should put C sub V there. No, maybe I should put C sub P there. Forget it. Let the instructor grade it. I'll just put C nothing there, and then this is somewhat correct, but it's not completely correct. Just like it was a big interesting feature that U is a function of temperature only. When you get to S, is S for an ideal gas a function of temperature only? Is entropy of an ideal gas a function of temperature only? U is a function of temperature only. H is a function of temperature only. Hey, I like that bandwagon. I'm on the bandwagon. Let's jump on the bandwagon. A lot of students will jump on that bandwagon. And they'll say S is a function of temperature only. But is it? No. No, no, no. So they'll forget some terms out here. Now, there was a lot of work in Thermo 1 to come up with an equation like this or like this. You can just focus on this equation. This is used most of the time, but this is also very handy. And it says, oh, C sub P natural log of T2 over T1 minus R natural log of P2 over C. So it depends on how your temperature changes as well as how your pressure changes. All right. Do you remember this equation? Yeah? All right, very good. Now, we need to have some processes which were isentropic. What does that mean? They had no change in entropy. So for an isentropic process, we use this equation or that equation, and S2 minus S1 is 0. I can rewrite this equation as C sub P natural log T2 over T1 equal to R natural log of P2 over P1. True? I could then do this. I could put it like this. Does that make sense? And then I can use this long lost rule that A times the natural log of B is equal to the natural log of b raised to the power a. What? Is that true? So this is equal to the natural log of P2 over P1 raised to the power R over C sub P. Now I have the natural log and natural log on both sides. What am I itching to do? I'm going to take and exponentiate both sides. When I exponentiate both sides, you get T2 over T1 is equal to P2 over P1 to the R over C sub P. Somebody says, for an ideal gas, I remember that R is equal to C sub P minus C sub E. Excellent. So if I divide that by C sub P, this is really what it's going to be is, you can do it a couple ways. 1 minus 1 over K, or K minus 1 over K. So you can have that T2 over T1 is equal to P2 over P1 to the power K minus 1 over K. Professor, I have no idea where that equation comes from, but I love it so much. I'm going to use it day in, day out. Steam, I'm going to use it for refrigerants, saturated liquids. I just like this equation. Don't do that. Use it when you know you can use it. It's for an isentropic process for an ideal gas. All right. Well, yeah, that was this equation, wasn't it? Isn't it that equation? And yeah, these are the isentropic, ideal gas, constant specific heats. Those are the assumptions. You can derive maybe from this equation. And then maybe you can use these two equations to derive the last equation. There's a couple ways of doing it, but you can get all three of these relations. For this chapter, we like this one. We like this one for the study of the Otto and diesel cycle. Likewise, we like this one for the study of the Otto and diesel cycle. And when we get to the Brayton, later in this chapter, we're going to like that one. All right? So you're going to have to know which one and why and how to use it, but accurately. Okay? But there was a quick review here of getting there from Thermo 1. All right, let's press on. Where do you get the specific heats for air? Here's the air, typically around 300. These values, after you use them a few times, you almost memorize them. K is about 1.4. C sub P 1.005, C sub V 0.718. Yes, sir, you have a question?
For the original, you were telling us that I saw that it was 298. Did you want us to interpolate for 298?
No.
Or just use it?
No, come on. Just grab it for that. Okay. Yeah. All right. I don't know if we have time for a problem. Should we, let's see, we got enough time, do we? Do we have enough time? Show of hands. Do we have enough time for a problem? Okay, we do not have enough time for a problem. Make sure your exam's in this stack. Raj, are you done grading? He has just a few, so please be patient with him. Maybe a few students help Raj spread them out on the table back there for people to pick up their homework as they leave. Thank you very much for your attention.